Hi everybody, it's Mrs. Gifford here for today's lesson on 0 to real numbers. And after this lesson, you should be able to clarify and use real numbers. So thinking back, we have both rational and irrational numbers. And within rational numbers, we have integers, whole numbers, and natural numbers. Natural numbers are the counting numbers, and then whole numbers take that list and add in 0. And then integers take that list and then add in the negative numbers as well. So let's look at some examples. Our first example is going to be to classify these real numbers, and I have this fraction, and I see that I have an integer over an integer, and as we've talked about, this is a rational number, because rational numbers can be written as integer over integer. And the other thing that we can do to prove it is we can take 5/22 and we can change that into a decimal, and if we do that, that becomes approximately 0.227, and the 27 repeats. So now let's move on to the square root of 81. What we want to do is think of, is there a number that we can multiply by itself to give us 81? And the answer to that is 9. And so not only do we say that this is an integer, but we also know that this is a natural number, because it's in that list of counting numbers. It's a whole number, and most specifically, it's an integer. Okay, and the natural numbers again are the counting numbers, and then the whole numbers add in the 0 in that list, and then the integers add in the negative parts. Now let's take a look at 56, the square root of 56, excuse me. And that 56 is not a perfect square, so it's not as easy as the square root of 81. So if we type that into our calculator, we get 7.483. There's no pattern. And it's not a terminating decimal. Whoops, that's an M, not an N. No pattern. And there's no terminating decimal as well. It continues, so then we know that this is an irrational number. I like to think of irrational, somebody who's irrational is kind of crazy. An irrational decimal or a number is a number that comes out as a decimal and there's no pattern, it's not nice and neat, it's not methodical with having a repeat, it's just a crazy number. So let's look at this next example. We're going to take a look at these lists of numbers and we're going to graph each set. This first one I notice in this set notation, these little brackets here, make this what we call set notation. And I see that all of my little, my fractions here are all having thirds. So what I'm going to do is number my number line. With fractions of thirds. 5/3, 6/3 would be 2. And what I'm going to do is I'm going to place a dot at each of those numbers. So our first number is -4/3. So I'm just going to put a dot right there on -4/3. And then I've got -1/3. And I've got 2/3 and 5/3. Now, one thing I want to point out that I didn't mention as I was doing this is that -1 is the same as -3/3. And then 1 is the same as 3/3, obviously, and then 6/3. So that's where those whole numbers came from with those fractions. So when you're given a data set, just put those points right on the list. Now, these next 3 examples are all examples of inequalities. Okay, we call these symbols right here inequalities. The easiest thing to try and do is to have the variable, the letter, in this case x, in this example, to be on the left-hand side. And we say this as x is greater than -2. It's greater than -2. It's not saying that it's greater than or equal to. Because it's only greater than here, we are going to use an open circle to represent that. So I'm going to go on my number line, and here's my -2. I'm going to put an open circle. And then because we're talking about the numbers that are greater than -2, we also know that any number to the right-hand side of that dot is going to be greater than. One thing that you can remember is if you have the variable on the left-hand side, the inequality symbol is pointing to the direction of what the direction that we want to shade. Our next example is also another inequality, and this one is a little different, not only because it has this less than symbol in there, but it also has a half of equal sign. So this is the less than or equal to symbol. And because of that equal sign there, not only are we going to have this little circle, but we are also going to shade it in because b can be equal to 4.5 and it can be less than 4.5. Let's see, so here's 4 and 5, so here's my 4.5. I'm going to put a closed dot there. And now what direction is that inequality symbol pointing? It is going to the left. So then I also know that b is any number that is less than or equal to 4.5. Now my last example, we have h is greater than or equal to -3 and 2/5. If I saw this fraction, I might change that 2/5 to a decimal, and so I know that that is -3.4. Again, we have greater than or equal to. Because this equal symbol is there, we are going to use a closed dot. So I'm going to go to -3.4, which is just less than halfway. I'm going to put a closed dot. And now in this case, we need to go to the right because that symbol is pointing to the right. So again, that means any number greater than or equal to -3.4. All right. Next example, we need to simplify these square roots. So the first thing I need to look at here is I'm going to simplify them. Again, square roots mean what number times itself makes 49. So if we can think about that, you ask yourself, well, 49 is a perfect square. So 7 times 7, and 256 is also a perfect square. 16 times 16. So then that means the negative square root of 49 over 256 is -7/16. Okay? You just pull one of those two numbers out and then you can get rid of the radical symbol. Now, pause the video real quick and try the second one on your own. Okay, so let's take a look at this one. We have square root of 4 over square root of 121. Again, 4 and 21 are each perfect squares, and what number times itself makes 4? And what number times itself makes 121? So then I know the square root of 4 over 121 is 2/11. So that is my final answer. All right, our last example here, we need to estimate each of these two square roots. And we were just talking about perfect squares. And so now we need to try and estimate where the square root of 15 would be. So I want to think of perfect squares. So I know I have 4, 9, 16, 25, and I'm going to stop because I know that 15 falls between 9 and 16. Okay, so then I say to myself, well, the square root of 9 is 3, and the square root of 16 is 4. And so because the square root of 15 falls between those two numbers, whoops, I forgot my 4, I know that the square root of 15 has to be between 3 and 4. Now, 15 is closer to 16, so I would say if I'm going to put this on a number line, and I'm going to put my 2, that's the square root of 4, a 3, that's the square root of 9, 4, square root of 16. And now I'm going to graph where the square root of 15 would be, and I know it's going to be a little bit closer to 4 because 15 is closer to 16. And then what we can say here, and we can write this as an inequality, and so we can say that the square root of, 3 is less than the square root of 15 is less than 4. So what we are saying is that the square root of 15 falls between 3 and 4. Now, let's do it again for 130. If I'm thinking of perfect squares, the first one that came to my mind is that I have the square root of 100, the square root of 121, and the square root of 144. Well, as I'm thinking about this, I know that the square root of 100 is 10, the square root of 121 is 11, and the square root of 144 is 12. Well, the good news is I have a square root of 130. So just like our first example, we know that the square root of 30 is going to fall between the square root of 121 and the square root of 130. And so what I'm going to do again is just make my number line. And I've got my 10, my 11, and my 12. And so from here, I am going to place my square root of 130. It's actually a little bit closer to middle than the other one, so you can just make your estimate. There's my square root of 130. And then we can write an inequality for this one. So what do you think it'll be? Right, it'll be 11 is less than the square root of 130 is less than 12. So now that we've had our 4 examples, now's the time for you to write a summary. So we want our summaries to be anywhere kind of between 3 and 5 sentences. So we've got it started for you, and you're going to fill in the blanks looking back at the notes that we wrote. So real numbers can be classified as either blank or blank. Natural numbers are blank, and an example is. And then you're going to continue to write these sentences down and fill in the missing blanks. So there you have your lesson on 0 to the real numbers.